chapter summary. Chapter 8, torque and angular momentum. So this is the chapter summary for chapter 8 from Giambattista's College Physics, 5th edition. Let's get going. Let me go ahead and say torque, angular momentum. There is a ton of stuff here. I mean, I think that maybe this shouldn't even be in one chapter. I think torque of itself is hard enough. Angular momentum, it's just a lot. It's just a lot. I'm just going to say that. So if you get through this whole thing, I want you to give yourself a high five. It would look like this, where you just do that. Some people call it clapping. I call it self-high five. Okay, let's just jump right into it. They start off, and they just say, hey, what if I have an object that's a disk, and it's rotating with some angular velocity omega? Well, then that should have kinetic energy. And they say, yeah, it does. We call that rotational kinetic energy. And they say, oh, it's 1/2 I omega squared. And then you would say, what is I? I know what omega is. That's the angular velocity. But what's I? And they say, well, I is the sum over all the masses, mi ri squared. And that doesn't really make sense. So let me just tell you, I don't think you will probably not actually calculate moments of inertia. You'll be given them for certain shapes. And I'll show you what they are. Let's just compare this to the kinetic energy of a point moving. And I call that kinetic translational. And that's 1/2 mv squared. Well, so we have 1/2, we have 1/2. We have angular velocity, we have velocity. And then we have I, and then we have m. So I is like the rotational mass. Does that make sense? And we're going to get into that in more detail later. But it's essentially a measure of an object's mass and how it's distributed, right? Because I can have two objects with the same mass, but if the positions of those masses are different, then it's going to have a different moment of inertia. And in fact, I'll just go ahead and tell you. Suppose that I have these objects. I have a disk. And it has a mass m and a radius r. That has a moment of inertia, we call that the moment of inertia, rotational mass, of 1/2 mr squared. If I have a ring, same mass, same radius, but there's nothing in the middle. That has a moment of inertia of mr squared. What if I have a sphere? It looks like, see, now it's a sphere. Then I is 2 this mr squared. You can't calculate these things. You need calculus to do them. What if I have a stick of length L, which is a bad choice, and it's rotated about the end? Then I is 1/3 ml squared. Now, if you rotate about the center, it's different. So I'll put a dot right there, dot, dot, dot. I 1/12 ml squared. You can try that. Get a stick like this and hold it from one end and try to rotate it back and forth. Like you would if you're shaking an object back and forth, that's a measure of its mass. If you rotate it back and forth, that's a measure of its moment of inertia. So if you rotate it back and forth like this and then try it in the middle, it's much easier in the middle. Don't do it with a pen. The pen's too small. Get like a good stick, a good stick. So that's moment of inertia. But we start to see this thing. We have rotational kinetic energy, translational kinetic energy, mass, rotational mass. So I'm starting a little sheet here because we've already done this before. We have linear quantities with their corresponding rotational quantities. So this is my connection between linear and rotational quantities, angular position, angular velocity, angular acceleration, alpha. We have the linear kinematic equations. We have rotational kinematic equations. We have the definition of average velocity, change in x with respect to time. Definition of average angular velocity, change in theta with respect to time. Definition of the linear acceleration, change in velocity with respect to time. Definition of angular acceleration, alpha, change in omega with respect to time. Now let's go ahead and put k equals 1/2 mv squared, translational kinetic energy. K r is 1/2 I omega squared. I should probably put up here m. I'll put a line just so we can keep it. I equals sum over I MIRI squared. It doesn't really matter what that equation is. I don't think you're going to use it. Okay, so that is the moment of inertia. When we deal with rotational objects, then we need the moment of inertia. We need the rotational mass. Okay, we'll come back to this when we add things on there. Torque and angular momentum. Torque. This one's big. And even then, the book lies. It's fine, because real torque is actually a little bit more complicated. But if you get a wrench, I'm trying to draw this, and you want to rotate that bolt. Well, if I push with the force there, or if I push with the force there, I'm going to get different amount of rotating ability. And this is what we call torque. Torque, which we use the Greek letter tau, is like rotational force. Now, the torque depends on three things. It depends on the force, how hard you push. It depends on how far that force is from the point of rotation, and it doesn't even have to rotate. And it depends on the angle between F and R. So we can write torque as RF sine theta. Now, sometimes we actually like to write it like this: R perpendicular F, or RF perpendicular. So suppose I push with the force right here, F. I could use the perpendicular force. So here's my R, and I could use just that component right there. And it's the same thing as F sine theta. Or I could say, well, what about if I draw a line perpendicular to this and use this for R perpendicular? And that's F perpendicular. It's all the same thing. So those are all the same equations for torque. Now, torque is actually a vector, but this book doesn't do that because it's really complicated, but torque's actually a vector. So we do need to take into account sine. Normally, we would say, I think they normally say counterclockwise is going to be positive. Clockwise is going to be negative. Because if you have more than one torque, you have to add them up. And then one other thing, point matters. So it depends on where, if I calculate the torque about this point and I calculate the torque about this point, they're different. So we do need to say the point of reference. They don't do that in the book, but I'm just letting you know, you do need to say what point you're referencing, especially if it's not rotating. If it is a rotating thing, then that point makes more sense. It's tough. This is tough, trust me. So this is in meters, that's in Newton, so torque is in Newton meters. Now, a Newton meter is also the same units as a joule, but this is just torque, Newton meters. Whew, I feel better just getting that off my head, my chest. But let's go ahead and put that up here. Linear F is force. The rotational force is torque. Torque. And it's RF sine theta. We're going to come back to that. I'm glad I made this little sheet. Okay, the next thing is equilibrium. Up until this point, we've been dealing with equilibrium by saying, oh, look, here's an object that has some forces acting on it, like this, maybe those three forces. And then I said the sum of the forces is equal to mass times acceleration, but at equilibrium, A is 0. So we got really usually two things. Some of the net force, I used F net. F net in the x direction is 0. F net in the y direction is 0. But suppose I'm going to use this laser pointer because I have it out right there. Suppose I have this laser pointer right here, and I push with equal and opposite forces like that. Then it stays at rest. It's in equilibrium. Everything's fine. But now what if I push with the same forces like here? It doesn't stay rotationally in equilibrium. So this is a point particle here, a point mass, but real objects are not like that. So if we treat a real object, although we will call this a rigid object because its shape doesn't change, for rigid objects, then we have another condition of torque. Torque net O is 0. And so this means that the sum of the torques about some point has to add up to 0. So we have an extra condition of equilibrium. So let's just draw an equilibrium situation. It doesn't really matter. I'm not going to solve a problem, but let's say I have a bar like this. I have the gravitational force acts at the center of mass. We talked about that in the last chapter, but it's better. There's a way to derive it using torque, and I will not do it in this video, but I'll make another video. So we have some force mg. Suppose I push with some force F1 right there, and then I push right here. Let's see. Push up. Let's push right here. I'm going to push like this, F2, just to make it fun. And then I'm going to have to also push with the force over here, F3. Because I have 3 conditions for equilibrium. The first is I need to pick an x and y axis, so let's just pick it right here. It doesn't really matter. So I can say F net x, what forces are in the x direction? It's just going to be minus F3 plus F2 x, whatever that x component is, and that's equal to 0. What about the net forces in the y direction? Well, I have F2y, I have plus F1 minus mg equals 0, because that one's not in the y direction. And then the torque equation, I have to pick. I'm going to put here, pick O. I have to pick the point about which I want to calculate the torques. You can pick whatever point you want. So you might want to pick something like right here in the middle. That might be better. If I do that, then torque net O, well, it's going to be the torque due to 1. I'll just write that torque 1. And that would be a negative torque, right? Because it wants to make it go clockwise. I have a torque 2 plus torque 2, which is negative. Yeah, this doesn't work. Okay, so let's just say this is down like that. How about that? So that's positive. Positive torque. So make it rotate this way. Now, the gravitational force exerts no torque, because if you push in the point through the point, then your R value is going to be 0, so there's no torque. And the same thing for this. It's just like trying to open a door by pushing on the hinge. It doesn't work. Okay, but the main point is in equilibrium for rigid objects, we get 3 equations to consider. The net force in the x direction, net force in the y direction, and the sum of the torques. And that makes it more interesting. And so I guess we could add that over here. Equilibrium, F net is 0, equilibrium. And then equilibrium, torque net, O, equals 0. Okay, moving right along. Like I told you, this is a big thing. So what if you're not in equilibrium? What if it's not rotationally in equilibrium? Then suppose we have this, and I have some point right there, and I push with the force, and it's not in equilibrium. In that case, I can write torque net O equals I alpha. So this is the total torque is the moment of inertia, the rotational mass, times the angular acceleration. Does that look familiar? Yes, it does. Let's go ahead and put that right here. F net equals ma. Over here, I have torque net equals I alpha. And remember, this is equal to m delta v over delta t, or delta p over delta t, where p is mv. And the same thing's true over here. This is I delta omega over delta t. That's alpha. And so I can write this as delta L over delta t, where L is I omega. I'm circling that, and I'm putting a box around that, because the name of the chapter was torque and angular momentum, and this is angular momentum. So if you think back to forces, saying forces change the momentum of an object, a net torque changes the angular momentum of an object. And you can see how nice that looks. Look at this. mv I omega. Mass, velocity. Rotational mass, rotational velocity. So it's really nice. This is a vector. I don't want to get into the vector nature of that right now because it gets a little bit complicated, but it is pretty cool. Now, if I have a net force of 0 on a system, then the change in momentum is 0. We call that conservation momentum. If I have a net torque of 0, then the angular momentum is constant. Conservation of angular momentum. I want to write that down, but I think I'm going to run out of room. Let's see, wait, what else do I have to cover? What else is in this chapter? I think that's it. Okay, so let's write that down. If F net 0, then P conserved. If T net tau O is 0, then L is conserved. Isn't that the whole page nice? I like that page, because it shows all this stuff and just a new way to do it. Okay, I do want to do one example, because they kind of talk about this in the book, but they use it as a homework assignment. But I do want to talk about this show you an example of conservation momentum. Suppose I have the sun, and I have some planet orbiting the sun like that, non-circular. So here it is over here, and here it is over here, at two different locations. We have this thing called Kepler's laws. That's a P. Kepler's, actually, second law. Kepler's second law says that as an object moves around the sun, it will, if you pick some time interval, let's see, like this, and you calculate this area, and then you come over here and look at this object, and during the same time interval, it's going to go further, but this area and this area are the same. But this is really conservation momentum, because as it's further away with a longer r value, then it's going to have a lower angular velocity. Over here, it's going to have a higher angular velocity. But we can see why this is the case, because angular momentum is constant. Why is angular momentum constant? Well, look at this. I have the gravitational force pulling on it this way, and here's my r value. What's the angle between those? Theta equals 180. What's the torque? It's going to be RF sine 180, 0. And the same thing over here. The force and the r are opposite directions, so the torque is 0. If the torque is 0, the angular momentum has to be constant. Now, how do we deal with, why does that make this speed up? Well, let's call this L1 and L2. L1 is I1 omega 1. Well, the only way to change the angular velocity is to change the moment of inertia. And if I just have this one point, then I can say I is going to be equal to m r squared. So this is actually m r1 squared omega 1. And then down at the other point, I have L2 is I2 omega 2 is m r2 squared omega 2 squared. And these two things are equal. So I get the masses cancel, r1 squared omega 1 equals r2 squared omega 2. That's it. So as r decreases, r2 is smaller. In order to keep the same angular velocity, omega has to increase. And that's why it sweeps around that faster. So it's one way to look at these astronomy kind of problems. They talk about angular momentum being a vector, but again, I think that's just too complicated for now. I will say one thing. If you have an object rotating this way, you can use the right-hand rule to find the direction of the angular momentum. If I take my right hand and I let my fingers curl in the direction of the velocity, the rotation, my thumb will point in the direction of the angular momentum. Okay, and that comes up sometimes. Because if you flip it, you would change the angular momentum vector. So if you want a constant angular momentum, it have to stay rotating in the same direction. Now that's not always true. There are some special cases in rigid objects that do really weird things that are awesome, but beyond the scope of this course. Okay, that's chapter 8. Like I said, it's a big one. I personally like where'd I put my little sheet? I had a little sheet there. I like that sheet, and I like the best thing in here that I like to focus on are the equilibrium problems. Torque net of 0. Those are really fun. The end.